So this is Emilie Fox and Sarah Petit. We are both from Block 1 Chem. This is for the AP Chem CCA. The problems that we were assigned to us are page 394, number 52, page 492, number 96, and page 231, number 127. These problems vary from calculating to theory and conceptual problems. We hope to explain the problems thoroughly and hopefully get 100. Enjoy the show.
Our first problem is on page 394, number 52. This problem states, for each of the following groups, place the atoms and/or ions in order of decreasing size. In this case, this problem is based upon the idea of atomic radius. Atomic radius is how relatively large an atom or ion is. There are three main steps to take in order to solve the problem. Step 1 is looking at the electron configuration for each element given or ion given. Electron configuration shows the different orbitals or electrons that each atom or ion contains. This is the primary method for solving a problem like this. The highest quantum level, or the highest number next to the largest orbital, determines how large the atoms or ions are. The higher the quantum level indicated by the higher number means the radius is larger than an element or ion with a lower number. This is the most reliable way to determine how relatively large an atom or ion is. However, if two atoms are in the same quantum level, Step 2 would be to determine which has the least number of protons. Protons have a much greater pull on the radius of atoms and ions, much more than electrons. Therefore, in this case, protons will significantly impact the radius while electrons typically don't. More protons means more pull in a smaller radius. Fewer protons, therefore, equals a larger radius. Ions take upon the same rules as atoms. However, the main difference with ions is that they can have the same quantum level and the same number of protons. Step 3 would be to look at the charges of the ions that fit this description. Only now does the number of electrons determine the size of the ion. The ion with the greatest number of electrons will have more pull in the nucleus, making it larger. This problem uses these three steps in order to list the ions and atoms in order of greatest to least in atomic size. Part A gives us V, V2+, V3+, and V5+. Without even looking at the periodic table, we know that these ions and atoms will all have the same quantum level and protons because vanadium is at the base of each of them. We must now look at the number of electrons in order to determine the order for these ions from greatest to least. Since all of these are cations except for V, we can determine that atomic V is the largest, so it is not losing any electrons like its counterparts. We can count down from there, giving us a solution of V, V2+, V3+, and V5+. Part B gives us Na+, K+, Rb+, and Cs+. Looking at the quantum levels that these ions are in, based on the periodic table, we can easily place them in order as Cs is at level 5 due to the lost electron, making it the same quantum level as Xe in electron configuration, Rb at 4, and so on based on the period. Therefore, from greatest to least due to quantum level, the answer would be Cs+, Rb+, K+, and Na+. Part C gives us Te2-, I-, Cs+, and Ba2+. This one is a little less obvious, so we must write out the electron configurations for each ion. Remember the ionic charge too. Look how Te2- would end with 5p6, I- with 5p6, Cs+ with 5p6, and Ba2+ as 5p6. Since they'll have the same quantum level, the one with the most protons will be the smallest, and the least with the biggest. Therefore, based on atomic numbers, the order is Te2-, I-, Cs+, and Ba2+. Part D is similar to Part A, in which all ions given have the same base, with P, P-, P2-, and P3-. When concerning ions with the same elemental base, more electrons means a larger radius. P3- would be the largest, while P would be the smallest. Thus, the order would be P3-, P2-, P-, and then P. Part E is similar to Part B, in which O2-, S2-, Se2-, and Te2- will all be at different quantum levels. As you can see, each is located in a different period, giving them different quantum levels. Those with the highest levels will have the larger atomic radii. Therefore, the answer would be Te2-, Se2-, S2-, and O2-. This concludes page 394, number 52.
So our second problem is number 96. The problem says the molar heat of fusion of benzene is 9.92 kilojoules per mole. Its molar heat of vaporization is 30.7 kilojoules per mole. Calculate the heat required to melt 8.25 grams of benzene at its normal boiling point. Calculate the heat required to vaporize 8.25 grams of benzene at its normal boiling point. Why is the heat of vaporization more than 3 times that of fusion? So for the first part, it's calculate the heat required to melt 8.25 grams of benzene at its normal boiling point. The equation we want to use is E equals delta H times moles. So we don't know moles, so we need to calculate that, and the equation for that is moles equals mass over molar mass. The mass of benzene is given in the equation, which is 8.25 grams, and the molar mass of benzene is 78. Then when we divide 8.25 by 78, we get 0.106 moles. Then we plug that into the equation, and we get E equals 1.05 kilojoules. For the second part of the equation, it states, calculate the heat required to vaporize 8.25 grams of benzene at its normal boiling point. We want to use the same equation, E equals delta H of vaporization times moles. Moles we calculated in the last step, which is 0.106. We then plug that into the equation, which is E equals 30.7 times 0.106, which equals 3.25 kilojoules. The last part of the equation is, why is the heat of fusion 3 times less than the heat of vaporization? Well, the heat required to separate molecules when moving from liquid to gas is much greater than if you were to just decrease the separation. As we go from left to right, the energy increases as we go up from solid to liquid to gas. And that is how you solve number 96.
Our final problem is on page 231 and is number 127. The problem states, a 15-liter tank is filled with H2 with a pressure of 2.00 times 10 to the second atm. How many balloons, 2 liters, can be inflated to a pressure of 1 atm from the tank? Assume there is no temperature change and that the tank cannot be empty below 1 atm pressure. This problem takes multiple steps and has a strong focus on gases, specifically the ideal gas law. The ultimate goal of this problem is to figure out how many moles of H2 are within the gas tank, and then how many moles of H2 it takes to fill a balloon to 1 atm, while making sure the primary tank doesn't get below 1 atm in pressure. To start off, the ideal gas law is PV equals nRT, and it will be used to help us solve this problem. P stands for pressure, in this case atm, V stands for volume, in liters, and is the number of moles of a substance. R is the ideal gas constant, which for ATM is 0.0821 atmosphere liters moles Kelvin, and T is temperature in Kelvin. In this case, we can ignore temperature, as it's consistent. In addition, it is well known in a rigid container at a constant pressure and at a constant temperature, pressure and quantity will be proportional as well, further showing how temperature can be ignored. As aforementioned, there are multiple steps to solve this problem. First, we will be finding the total number of moles within the tank. Then we will find the number at 1 atm and subtract the number of moles available to fill up the balloon since we can't go below 1 atm. Next, we will find the number of moles needed for each balloon to fit the requirements, and then divide the number of moles available by that to get the number of balloons that could be filled. To find the total number of moles in the tank, use PV equals nR and ignore T. P is given as 200 atm, V is given as 15 liters, and R is always 0.0821 atmosphere liters moles Kelvin. Multiply 200 atm by 15 liters to get 3,000, and divide this by the ideal gas constant to isolate moles. The total number of moles is 36,540.8039. Next, find the number of moles left in the tank at 1 atm for pressure. P is placed as 1 atm, V is 15 liters, and R is the ideal gas constant. Multiply 1 atm by 15 liters to get 15, and then divide by the ideal gas constant to get 182.704199 moles left over. Subtract this from the original total to get 36,358.09988 moles available for us to use under the constrictions of the problem to fill the balloons. After this, find how many moles each balloon needs to be 2 liters in volume and 1 atm in pressure. Using PV equals nR and ignoring T, plug in the values given, including the ideal gas constant to solve for N. so each balloon would take 24.3605393 moles. Since we know that we have a total of 36,358.09988 moles for use and 24.3605393 moles for each balloon, we can divide the first value by the second value to see how many balloons could be filled. By doing so, we solve that 1,492.5 balloons can be filled. Since you cannot have a half balloon, 1,492 balloons can be filled while keeping the main tank above weight ATM and pressure. Due to significant figures, as only 3 significant digits are used within the problem, only 3 can be left in the answer. Therefore, the final answer would be 1,490 balloons. Well, that's all from us. We hope that you enjoyed our video. Thanks for watching. Bye!